In this lesson, we will define complex numbers and perform operations with complex numbers. Also, we will define the complex conjugate pair theorem and apply it to solve problems. First, we are asked to show that x equals 3 is a root of the polynomial function f of x equals x cubed minus 3x squared plus x minus 3. And then we're asked to find its complete factorization. So first we take the coefficients of the polynomial we're given and we synthetically divide by 3 to show that we get a remainder of 0. The coefficients of the depressed polynomial are 1, 0, 1, which means that the depressed polynomial is x squared plus 1. So the factors of our polynomial are x minus 3 and x squared plus 1. You might remember from Algebra 2 that x squared plus 1 is a sum of squares, which means it's an irreducible quadratic. What is an irreducible quadratic? It's a quadratic that cannot be written as a product of linear factors with real coefficients. In other words, it's a quadratic that has no real zeros. And this makes sense if you think about the graph of x squared plus 1. The graph of x squared plus 1 is an upturned parabola with a y-intercept of 0, 1. Well, what if we could figure out the roots of x squared plus 1? Let's just try setting x squared plus 1 equal to 0 and solving for x. So if we say x squared plus 1 equals 0, and then we subtract 1 from both sides, we get x squared equals negative 1. So we need a number whose square is negative 1. Well, that's a problem because there's no real number that squares to give negative 1. But what if we made up a new kind of number with this property? Let's define I to be the number whose square is negative 1. So we write I squared equals negative 1, and we call I the imaginary unit. Also, we call any number whose square is a real number that is negative an imaginary number. For example, 5i is an imaginary number because its square is negative 25. If we look at 5i squared, that's equal to 5 squared I squared, which is equal to 25 multiplied by negative 1, which gives us negative 25.